Welcome to an exploration of the quantum mechanical model of the atom, the modern foundation of our understanding of matter. To appreciate this revolutionary model, we must first look at what came before it and why it failed. The Bohr model was groundbreaking, proposing that electrons orbit the nucleus in fixed, defined paths like planets around the sun. While the Bohr model successfully explained the spectrum of hydrogen, it completely failed when applied to atoms with multiple electrons, showing a fundamental flaw in its fixed orbit assumption. The resolution to this limitation came from a radical new idea, that matter, like light, has a dual nature. Louis de Broglie hypothesized that if light can behave as both a wave and a particle, then particles like electrons should also exhibit wave-like properties. This concept, known as wave-particle duality, means electrons cannot be treated as simple solid spheres, paving the way for a probabilistic model. This new quantum view of the atom relies on two key principles that govern the behavior of subatomic particles. The first is the Heisenberg Uncertainty Principle, which profoundly changes how we define an electron's location. It states that the more precisely we know an electron's position, the less precisely we can know its momentum, and vice versa. There are fundamental limits to simultaneous knowledge. The key mathematical framework for the new model is provided by Schrödinger's Wave Equation. This complex equation describes the behavior of the electron wave within the atom. Its solutions are the quantum numbers we use today. The wave function itself doesn't give a definite path, but its square gives us the probability density of finding the electron at any point in space. This shift from fixed paths to probability leads directly to the concept of electron clouds and atomic orbitals. We no longer speak of an electron's precise orbit, but rather a region of space where finding the electron is highly probable, which we call an orbital. The simplest orbital is the s orbital, which is spherical in shape, representing a uniform probability cloud around the nucleus. Next are the p orbitals, which take on a dumbbell shape and exist in three orientations along the x, y, and z axes. The d and f orbitals introduce increasingly complex and multi-lobed shapes, which are crucial for understanding the bonding of transition metals and intertransition elements. The quantum mechanical model marks a true paradigm shift in atomic theory. We moved from predictable orbits to probabilistic clouds governed by wave mechanics and the inherent uncertainty of the subatomic world. This model is not just a theory. It is the fundamental framework that underpins modern chemistry, materials, science, and physics.